Hi, I am Eduardo Pena, and this talks about fast algorithms for denial constraint discovery. This is joint work with Fabio Porto and Felix Neumann. So one of the motivation for using denial constraints or DCs is to capture data quality rules. Whenever we have a table, relational data, we want to improve the data quality, right? So data quality rules help in that. So here we have three examples of simple data quality rules. The first one says each employee has a unique value of ID as a unique constraint. The second rule says employees cannot supervise their own supervisor, a rule that spans different columns. Or the third rule, a typical data cleaning rule that states for any two employees from the same department, the one that was hired first should not earn the lowest salary. So there are different formalisms to capture such rules, such data quality rules. We are interested in denial constraints because they have a high expressive power. They generalize keys, functional dependencies, order dependencies, and so on. They are able to capture most of the data cleaning rules we find in practice. These are easy to understand. The idea is to have a predicate conjunction that cannot be true. So here we have some examples. The idea is to express relational predicates that compare tuples on some columns or column pairs. And DCs can be easily translated into SQL queries, such as this one, a self-join query. And once we run such queries, we will find DC violations, tuple pairs, for example, that violate a DC. And that violation is a potential data error. We can try to repair the database for that error using data cleaning solutions. There are many of them that work quite well. But in this paper, we are interested in discovering the DCs that hold in the data set. Suppose we have a data set of a complex domain that we do not understand, and we want to identify which DCs hold in that data set. Maybe the data set has a lot of rows or columns, so it's difficult to specify the rules by hand, so we want to discover them automatically. And why discovering the DCs is challenging? Well, each column of the dataset might generate a set of predicates. These predicates might involve different operators, a column or a column pair, and that will generate what we call the predicate space. Here we are represented with P. And any subset of the predicate space in principle could be a valid DC. So we have a very large space, and checking each of the DC candidate is expensive because of the range predicates or the different types of predicates that might exist. So we don't want to do that. In the past, a three-phase DC framework was proposed that works quite well and has been used in subsequent work. The idea is to build a predicate space or defining which predicates can be used to define DCs. That's quite straightforward. And then the second step of the framework is to build an auxiliary data structure called evidence set. The idea is to go through the tuple pairs of the data set and define which predicates each tuple pair satisfy. And with the evidence set, we can enumerate the DCs because the process is quite similar to the minimal cover search or hitting set enumeration for the evidence set. So in this work, we contribute to novel algorithms that are much more efficient than the previous solutions for both evidence building, but also for DC enumeration. Of course, I'm not going to get into the details of each technique. I'll just highlight some of them, but please check the paper for more details. So one of the the main ideas of the paper is called evidence contexts. And the idea is to capture the redundancy that happens in the evidence regarding a data set. So in this example, we have the evidence for tuple number 4 for T4, and we see that all the evidence computed is the same. So there is a lot of redundancy. And in production data set, that kind of redundancy also existed and is quite high. And previous work would either compute that evidence or either need to iterate or hash such evidence individually. So what we are doing here is that we are simply using a much more compressed structure to represent the evidence. That's what we call the evidence context, given a tuple and a tuple set. So when we combine these tuples from a tuple with any tuple in this tuple set, we produce an evidence. And what we want to do is to represent this in a compact manner. So we have fewer integers, and we also have compression potential. And with this representation, we also have an information called evidence multiplicity that will help to discover what is called approximate denial constraints. There are denial constraints that hold for most of the data. Sometimes we are interested in approximate DCs because they can accommodate errors or data exceptions. So how can the evidence context be computed? So we use two principles. The first one is the evidence ahead principle. Here we initiate the evidence context with the predicates of low selectivity. The intuition is to start the evidence context close to the final state. So most parts of the evidence context is already correct. But of course, there will be parts that are not correct. So what we devise algorithms for what we call evidence context reconciliation. And these algorithms will fix the complementary operators or the complementary predicates. We do this for each predicate group that are set of predicates that share the same column. So in this example, we are handling the evidence context for tuple T1. And when we check these context for P1 and P2, we see that everything is fine. Tuple T1, when combined with T2, T3, and so on, actually satisfy the predicate P2. But once we go for checking the predicate group on name right here, we see a problem regarding T1, T5, and P4, because T1 and T5 have the same value of name, so this part does not satisfy the P4. So we need to do something about it. So that's why we need the reconciliation. And the idea with the reconciliation is to move parts of the evidence context, such as the evidence, this right side right here, and also the tuples from here to here, and so on. And as we can see, there's not much data movement due to the predicate selectivity, the evidence ahead idea that we discussed before. And that's one of the reasons the algorithms proposing this work are much faster than the previous ones. It's about data movement. So the algorithms they can perform many operations fast, and these operations work on small parts of the data. So how can we implement this reconciliation fast? So we use a pipeline, or what we call evidence context pipeline, that process the evidence context predicate group by predicate group that are predicates sharing the same column set. And in each stage of the pipeline, we will have specialized algorithms and data structures that help handling the complexity of each predicate type. So because we consider the evidence ahead principle, we only need to handle the equalities because we assume that all evidence contexts would satisfy the different them. So we need to check for the counterpart, right? And for that, we use algorithms that are quite similar to hash joins, but they use a lot of logical operations on bitmap indexing. Uh, for the complementary regarding the range, range operators, we only need to consider the less than case. And for that, we extend the equality algorithms, but we also use sorted bitmap indexes using basic trees. And also we devise a binning technique for handling columns of high cardinality. Finally, there are some heuristics described for improving the compression of the evidence context and the performance in which which the operations inside the algorithms can be achieved. So once we compute the evidence set, we can start enumerating the DCs. So a quick overview of how can we do so. In the paper, we describe the idea of predicate subspace, that is to use to enumerate the DCs for each predicate individually, but in doing so, we reduce the amount of evidence that we need to consider. And so once we compute the evidence of every predicate, once we compute the DCs regarding every predicate, we can go to a step of minimization. So we can remove all the non-minimal DCs at the late in the stage. And there are other techniques as well, such as indexing for filtering the evidence. Those techniques go inside the algorithms. So all these techniques can be combined with the previous solutions for DC enumeration, and these techniques help improving the performance of all these previous algorithms. So our results show that for evidence set, the techniques improve the performance of this enumeration a lot. So here we have that we compared our solution to the previous to the fastest algorithms that existed at the time. So what we see is that Hydra, for example, has a hard time when the set of the Cs is large, and DC Finder performance is penalized when we have a lot of records. The evidence context pipeline, that's the solution we propose in this work, is more stable, and it's often orders of magnitude faster. So for the DC enumeration, we have a similar trend in the sense that once we use the techniques we propose in the paper, all the previous algorithms can be improved by up to orders of magnitude. So that's a quite improvement over the state of the art. So our final thoughts is that denial constraints can help in data quality, as they can reveal critical errors in data. They can help other data management tasks as well. So discovering the DCs are quite challenging, but there are solutions out there that can help in the task. In this paper, we devised a solution that is called evidence context pipeline for the evidence set building. And then for the DC enumeration, we devised hybrid algorithms using different techniques that help discovering all the DCs fast as well. So check out the paper for more information. Thank you.